So hi everyone, my name is Gia. I'm a first year PhD here in biomedical engineering. So my concentration is all about tissue engineering and biomaterial. So today we're in the class of tissue engineering. So I'm wondering who is also taking biomaterials because they are kind of connected to each other. I think there is one TL there. It's for biomaterial. Okay. So my project is about targeted drug delivery system for chronic spinal cord injury. It is known that the spinal cord injury happens a lot while you have car accidents or violence, and contusion model is one of the most common model in spinal cord injury. And after the contusion, your spinal cord will get inflamed, so that your I think you know what is the structure of the spinal cord, right? So the center of the spinal cord will get inflamed, and then it will gradually disappear after 7 days. So you want to save the spinal cord. How are you going to do that? You want to use the drug of anti-inflammation. Then the problem is that the spinal cord was protected by a membrane, so that the fluid is kind of less coming into that spinal cord, the fluid that will attach to the spinal cord that has been injured. So the thing you want to do is that you want to put something onto the spinal cord directly, delivering the drugs. So the problem is that, first, what can contain the drugs? Because you know that if you inject it or administrate it, it will just go through all your bodies, and only a few of them enter to the spinal cord. So you want something to hold the drug. And when you hold the drug, you want to control the release of the drug, because if the drug is too much, then it possibly will be toxic to the cells or to the spinal cord that have already been injured. Like you take some salt and you take too much of it, and then you get, too dry or dirty or something. So, and then you want to, and then especially in vivo, there are some other response of the body that you want to take care of. So now, here is what we are going to do is to do biodegradable, which will degrade in the body. That will now it does not require after operation care, or after the operation afterwards that have to take out the scaffold that you contain the drugs. And also you have to make the scaffold compatible, so that it will be accepted by your body. Now, I'm not sure if you've noticed that the tissue engineering is about solving problems. So the problem now, but I'm giving an example, is what? Is spinal cord injury. The spinal cord injury, so we have some current strategies. What is current strategies? The drugs. The drugs with anti-inflammation properties or antioxidant properties that can save the spinal cord. But what is the problem that? The problem is the drug does not enter to the spinal cord. So what you are going to do? Like what you have explained before, you have something that can contain the drugs, directly target the spinal cord and deliver the drug to that. And what is the further problem? How the drug be released? How are you able to control the release of the drug? And how does it act in vivo, in the body? So that's what you are going to consider. So tissue engineering now, I have already explained, it's about the material that you are going to use, and the drug or other things that you are going to use, and the place that you are going to save. So we're going to, I'm going to give you another example so that you can know a little bit more about this tissue engineering. Now, you have a tendon. You know what is tendon? It is a connective tissue, a band of connective tissue that connects the bone and the muscle. And it can withhold the tension, right? So now this is a tendon. Let's say it's an ankle. And now it get ruptured. normally it will happen in like athletes or older people. What are you going to do? First of all, just let it grow back to themselves. But it will like take years, months or years, because like older people have like lack of like regeneration or something. And what else? You suture them, right? So you cut them and you suture this part and this part together by surgery. But what will bring you the problem? Like what does the surgery always bring a problem? Complications, right? And after you cut this, especially for athletes, it will really give them like severe dysfunction or malfunction after the surgery. So it takes years for them to recover, and probably they won't do it athlete again. So what are we going to do? Still we have this. So still this is the rupture. So what we're going to do? We're going to put some scaffolding here so that it can connect this and this. And you have to make sure that the scaffold here is able to help let the cell ingrow, because you finally want the cell to connect themselves so that it will become a complete tendon again. So you want the scaffold to let cell grow. So now it's come to the biomaterial part. The biomaterial part tells you what is the property of the material. Like the material first for tendon, you know that it can withholding the tension, so the material has to be strong. So the material has to be strong, and you have to be aligned because the tendon is aligned. So you have to make sure that everything follows what tendon is. And you have the cells. So the cells you're going to choose. So the first is the scaffold. And the second is the cell, right? Because they going, if you let the tendon grow themselves, they will take years. But if you put some cells in it, like to help the growing or like to connect both sides of this tendon, then probably it will come faster. The second is cell. And how are you going to choose the cells is what you're going to discover. You have to read the literature, like what people are usually do, like they will choose stem cells and they will differentiate it, or they will just choose the tendon cells to put into the scaffold and let it do. And the third thing, like just as said, if you are choosing the stem cells, you know, so the stem cells are like, what is the stem cells? I think somebody in bio should know what is stem cells.
It's like undifferentiated cells. Right?
Yes, but you have to make it differentiate, right? You have to differentiate it into the certain cells that you want. So what are you going to use to trigger them, to differentiate them? You have some certain of drugs or certain of like extracellular molecules that have to differentiate the cells. So the third thing is that you have to use the drugs or reagent that will differentiate the cells or promote the cell growing or proliferation. So these three, and the drugs, you don't want the drug to be too much, like, and it will like hurt the tissue. You don't want the drug to be so less that it does not help that much. And you don't want the drug to be released so quick, like in one day, and then the cell does not grow very well, and then it just disappears, and the cell does not have like enough functioning reagents or functioning nutrients in it. So these are the problems that you have to solve. This is all about engineering, tissue engineering. Am I clear? Okay, thank you.
Any questions? What things are used for scaffolds? Like what kind of materials are used for scaffolds?
Like hydrogels. Like you have different kind of hydrogels or material, biomaterials. I might say that have like porosity and moisture that can mimic the in vivo environment, mimic the tissue that you want to make. Yes.
So is this different from the spinal cord injury scenario in that this scaffold doesn't have to dissolve afterward?
It better dissolve because you don't want to cut it open to put out the scaffold afterward. Any other questions?
Oh, I have a question.
Yes.
I have another question. So you said one of the problems with using the drugs to induce differentiation is that you could have dosage problems, right? Like you said, you don't want too little so that it doesn't happen. You don't want too much so that it's toxic to the other cells.
Yes.
Couldn't you circumvent that problem by exposing the cells to the drug before you insert them into the
Yes.
brain stem?
Yes, it is possible that then the problem will be then you probably then will just differentiate that into a tendon cell, right? And then you put that scaffold into the injury site. That is one way. The other way is also that you put the drug, put the drug together with the cell, the stem cell into the injury site. These are two ways. You choose what you want. But the thing is that you have to consider, like, if here we don't just need stem cell, need tendon cells. We need other cells, and they have like different differentiation behavior. What they're going to do. So that's the problem that you have to address or think about.
Any comments on the style of the presentation?
Good eye contact.
Oh, yeah.
Yeah, excellent. Excellent eye contact.
You have really good eye contact, but you use a lot of jargon.
Oh, sorry.
So I worked in injury models, so I understood some of it, but I don't know. There was just some. I mean, I use some too, so.
I like that you use a really relatable example, and I think the pictures are a good addition.
I think your posture was great. That's something that I think can be really difficult to do, but you seem very comfortable just standing straight and delivering. So that was really nice.
Thank you.
I wasn't sure sometimes when you were asking questions, like if you wanted us to answer them, or if you were just asking rhetorical questions.
I was like waiting for like a few seconds for you to respond,
Okay.
and then I only see like a few people nodding, but not like tend to speak. So I just move on instead of wait.
Because I think especially if we're not familiar with the material, it takes some time for us to be able to formulate questions, and then by that time you've already moved on.
Oh,
I
should
think-
give you more
So,
time.
yeah, pause for.
I think it's the same thing. Like, it seems like a long time up there, but from this end, I think sometimes there wasn't even like the opportunity to even like get
Yeah.
Okay.
like it was quick. So,
Okay. Thank you.
all right, nice job.